What's going on, everyone? In today's session, let's quickly recap what we talked about in terms of derivatives, and we're going to move on to assessing derivatives visually, okay? And so before, in previous sessions, we've looked at derivatives in terms of its definition, where we said that the derivative with respect to x, right, of some function f of x can be calculated by taking the limit as h approaches 0, right, of the function f assessed at x plus h minus the original function f of x, all divided by h, okay? And we said that f of x plus h just means that in whatever function you're given, wherever you see x, you're going to replace that with x plus h. And we said that f of x just represents your original function. Okay, so we went from here and we went to the power rule, or the shortcut version of a derivative, where we said that the derivative with respect to x of a function x raised to the n, right? In this case, x is your base, n is your exponent, and let's not forget that behind here there is an invisible 1, right? Because 1 x raised to the n is the same thing as x to the n. And so let's just keep track that 1 represents your coefficient, okay? Or the number behind the variable, or in front of the variable. And we said that taking the derivative with respect to x of a function x to the n is just equal to nx raised to the n minus 1. And we said we were able to get this by following 2 steps. The first step of the shortcut is to multiply your exponent multiplied by your current coefficient, in this case is 1, so n times 1, and that's going to give you your new coefficient. Step 2, you're going to subtract 1 from your exponent, current exponent, okay? And that's how we got our shortcut. For today, let's move on to visually approximating the curve of our derivative when we are given the curve of our original function, f of x, right? And so this curve is your curve for f of x, and I would like to get the curve of my derivative, right? It also looks like this. And remember, these two terms are the same, and you can use whichever one makes you more comfortable, f prime x or ddx of f of x, okay? And in order to go from the curve of f of x, right, which is plotted as x versus y, right, or x versus f of x, because like we've said before, y and f of x are generally interchangeable because y is generally a function of x, right? In order to go from this curve, we are now going to plot still x on our horizontal curve, on our horizontal axis, right? But on the vertical axis, we are going to plot slope, right? Also represented by m. Okay, and these are the same thing, they're interchangeable. And so the real first takeaway here is that if you're trying to go from the curve of your original function, right, to the curve of your derivative, right, your original function is going to be given to you in terms of x versus f of x, right? Or same thing, x versus y. The plot of your derivative, right, using this curve is going to actually be x versus the slope, okay, at specific points that you pick on your curve. And we're going to go through that with this example right here. Okay, so let's clear some of this stuff out and let's get started. Okay, so as we've learned before, right? Slope is going to tell you the steepness and the direction of the tangent line at a specific point on your curve. So when you're given the curve of a function, the first thing that I always consider, right, are peaks and troughs or pits, right? The reason why I consider peaks and troughs, in this case, it would be this peak at x is equal to -2, right? It would be this peak at x is equal to +2, and it would be this trough or this pit, right? At x is equal to 0. And let's write these down. Peaks and troughs are located at x is equal to -2, 0, and at +2. Okay, and the reason why I choose these spots first is because at these points, when you approximate the slope, which we know is defined as rise over run, right? We've seen it before, the change in the vertical direction divided by the change in the horizontal direction, right? When you look at rise over run, let's consider that at these specific points, right, just at these points, the tangent line to these points looks like this, right? Looks like this. Because it's touching that point and only that point. And so at this point, these tangent lines, they have some small run, right? They move left and right to some degree. But in terms of up and down rise, they have none, right? And so your rise in these cases are 0, which means that your overall slope at these points is 0, right? So at peaks and troughs, your slope is always going to be 0, okay? So now let's plot these points onto our derivative curve, right? This is our curve of the derivative. And so we said at x is equal to -2, -1, -2, at 0, and at +2, +2, we said that the slope, right, the m is going to be 0. So these are going to be 0. And these are going to be points that the curve has to pass through, right? Cool. After this, let's consider, and I'll leave those there, right? Now I want to consider regions or locations on my curve, right, where I can generally approximate the rise over run. Okay, you're going to eyeball this. And so I'm going to pick the places, and I'm going to write 2 down here. Okay, I'm going to pick spots where there's an increasing trend, right, in my curve. And so in this case, the curve f of x is increasing here. So I'm going to choose this location, right, or down here actually. Let me undo that. I'm going to choose, make sure that's a pen. I'm going to choose this location, right, because it's increasing. I'm going to choose this location again because it's increasing, right? And so let's consider those. So these points, x is equal to -3 and x is equal to +1, right? At -3 and at +1. So let's write those down. X is equal to -3 and at +1. And at these specific points, let's again consider the rise over run and see if we can't eyeball that, all right? So assuming that this is a beautiful plot that's consistent and that this increase, right, the angle and stuff is the same as the increase here, we're going to draw a tangent line to this spot, okay? And so that's going to look like this, all right? And the one here is going to look like this to some degree. And I'm going to erase these just to clear up some eyeball room. All right. So based on the steepness of this line and this line, you can tell that the rise is really high because these are really steep lines. And so let's just say we're going to approximate here, right? This is where we're going to start approximating, right? And you're going to approximate typically where you're evaluating increases and decreases on your f of x curve. So in this case, let's say this thing rises super fast. So let's say it rises 5 units, right? For every 1 unit, it moves to the right, okay? And so this would give you an approximated slope of 5, right? At x is equal to -3 and at x is equal to +1. So now that we have this approximation, let's plot that on our f prime x curve, right? So 5, right? 1, 2, 3, 4, 5. So we said that at x is equal to -3, we have a slope value, right? An m value of 5. And at +1, we have a slope value, an m of 5. Okay? Now, in order to finish this off, all we're going to do is consider our points at -1, right? And +3. So now we went from first looking at peaks and troughs where the slope is always 0. Then we considered where locations where our curve increased, right? Now let's consider areas where our plot shows a decreasing trend, right? And that's going to be here and here, right? At x is equal to -1 and x is equal to +3. So -1 and +3, okay? And so I'm going to erase the older lines again so that we can clear up some eyeball space in a minute. And so at these points, let's draw the tangent line. So the tangent line here, whoa, that might be a little bit off. So let's go here and then I'll move it closer. Awesome. And then we have one more here. Okay, but we're going to do that, okay? So now let's consider the slope of these tangent lines. And so again, we're going to do this just so that we kind of hardwire it, right? Rise over run, right? In this case, at these points, f of x is decreasing. So it's not rising, it's falling. And so that's going to give you a negative, right? And it's falling pretty quickly because this line is pretty steep, right? On the downturn, it's pretty steep. And so let's assume that it has the same angle, right? So let's say it's falling in this case, 5 units for every 1 unit that it moves to the right, right? And so in this case, that was another approximation. And again, approximations will typically occur where your function is increasing and where your function is decreasing, because we already know that at peaks and troughs, your slope is 0. Okay? So in this case, we said that our approximation for the slope is -5, right? And so now let's plot these points on our f prime x curve. So at x is equal to -1 and at x is equal to +3, we're going to go 1, 2, 3, 4, 5. This is -5. So at -1, we said our slope was approximated at -5. And again, at 3, our slope was approximated at -5. So now you have points, right, that we're just going to connect. So we're just going to connect them like so. Okay? And so now that's it. This represents the curve of the derivative, right, based on the curve you were given for your original function. And remember that when you're doing this, right, you're essentially plotting values of x versus the approximated slope at those points. All right? And so if you were able to do this one, right, let me give you an example that you can work on yourself, and feel free to pause the video and try to work on it. And then after you're ready, go ahead and play the video forward, and then we are going to work on it together. Okay? So in this case, you're going to try this example. Again, this is the curve of your original function. I'm going to put f of x. I'm just going to point it to this entire huge thing, right? So given the curve for your original function, try to approximate the slope at various points in order to figure out what your derivative looks like. And just remember that when you're plotting your derivative, you're plotting x, right, versus the slope. Right? So go ahead and pause it and give it a try. Awesome. So let's see what you got, and let's see if we kind of agree with our answer, right? And so again, our approach to this is that we are approximating, right, the slope at various x values, right? X values where we choose to evaluate. And so again, the first thing that I tend to do is that I'm going to consider peaks, right, and troughs or pits, right? Because at peaks like this one, and this one, right, and at troughs or pits like this one and this one, at all of these points, we know that the tangent line looks like this, right? It's supposed to be straight across. Looks like this, looks like this, looks like this, and it looks like this, right? And so we know that when we drop that tangent line there and when we evaluate, right, our slope, which is defined as rise over run, we know that there is some, right, there's going to be some type of movement left to right, but we know that there's no up and down movement here. There's no rise. And so we know that this goes to 0, and we know that at these points, the slope at peaks and troughs will always be 0 for all intents and purposes of what we're doing. And so let's plot that first, right? So if we take this to be -1, we take this to be -2, right? Over here, same thing, 1 here and 2 here, right? At x is equal to -2, -1, 0, 1, and 2, right? At all of these points, right, the slope is going to be 0. The slope of these tangent lines are going to be 0. So let's do that. So -2, -1, 1, 2. At -2, let me write these in. 1, 2. So at all these points, it's going to be 0. Now, right, after peaks and troughs, we're going to do the same thing at points where we see an increasing trend, right, of our function curve f of x. And so at this point, I'm going to clear out some eyeball room. And now we're going to pick increasing points. So we're going to choose this value, right? We're going to choose this value. We're going to choose this value, all right? And we're choosing these values, and I'm actually going to erase this one because I'm going to extend this one out to make it more intuitive. So we're going to choose this point, all right? And so at points where x is equal to, let's say this is negative 2.5, so negative 2.5. At x is equal to negative 0.5, right, a half, negative 0.5. And at x is equal to positive 1.5, positive 1.5. At this point, let's put in our tangent lines. Right? So tangent line is just going to touch that point on the curve. Same thing with this tangent line. And then same thing with this tangent line, right? And so let's, again, we're going to assume that this drawing is perfect and that every increasing line has the same angle and they're identical, right? And so when we are going to evaluate the slope at these points, which is defined as rise over run, right? These are increasing really, really hard, right? And so it barely goes to the right, but it's increasing a lot. So you know that your slope or your rise is going to be a really, really big number. You know that the run is going to be quite a small number. So a really big number divided by a really small number is still quite a large number, right? Because think of it as 100 divided by 1, right? That's still going to be 100. 100 divided by 0.00 something, something, something. It's still going to be a large number. And so in here, based on our approximation, right? Let's just say that this thing rises, it goes up 10 units for every 1 unit that it goes to the right, okay? And this is definitely an approximation. So here we can say we approximate that the slope here is 10. And so we're gonna plot that at x is equal to these coordinates on our f prime x curve, okay? So again, at x is equal to negative 2.5, which is here, right? 10, we're just going to say 10 is all the way up here, right? And so at x is equal to negative 2.5, we're going to have a point at slope is equal to 10. The same thing at negative 0.5, right? It's going to be positive 10. Same thing at 1.5, it's going to be positive 10. Once we have this, right, the last thing we're going to do is we're going to assess points where we see a decreasing trend, right? So a decreasing trend in our f of x curve. So now we're going to choose this point, and I'm going to try to choose a new shape. Shaded in triangle. X is equal to negative 1.5, right? Decreasing trend. X is equal to positive 0.5. And then if we extend this thing out, x is equal to positive 2.5, right? So these are the points that we're going to pick to assess. Negative 1.5, right here, positive 0.5, and then 2.5, 0.5, right? And we're going to assess the rise over run for the slope. And at these points again, you're not rising, you're actually falling. So in that case, it's going to be negative, right? And it's pretty steep if you were to put a tangent line to each one of these points, right? If you were to put tangent lines to each of these points, it's a really steep decrease, okay? So let's say that for every 10 units you fall, right, down, you're going to move to the right once. And this is an approximation. And so this is going to give you a slope, an approximated slope of -10, right? And now let's just plot that like we did before. So this is -10. So now we know that x is equal to -1.5. -1.5 is here. It's going to be -10. At positive 0.5, which is here, it's going to be -10. And at x is equal to positive 2.5, which is here, right? It's going to be -10. So now you have all your points, right? And all you got to do is connect them to 1. Okay, and it could be a little more round. But this is the concept of approximating the curve of your derivative when you are given the curve of your original function, f of x, okay? And remember that to do this, you are approximating the slope of the tangent line at points that you're gonna choose, okay? And we said that the best way right now to approach it is to first consider peaks and troughs, right? Because you know that there's no rise term, so your slope is always 0 at these points. Then consider a point right in the middle of an increasing trend, right? Such as these open circle places here. And then after that, assess places where you see a decreasing trend in f of x, okay? And so if you have any questions or comments, please leave them below and I'll get back to you as soon as I can, okay? Thank you.